Right. So welcome everybody to the public portion of Gabriela's PhD defense. It's funny because Sam was basically just mentioning, some of the story, and I just wanted to share some of the story with Gabriela because it was indeed like yesterday when Nick Stergulas, who was my undergraduate thesis advisor, told me that he was working with this phenomenal Italian student, and he's looking for a PhD and he doesn't know where to go. And so I strongly recommended him to you because I have never seen a student like this before. That's what he told me. So I was at Princeton at the time. Gabriela and I met on Zoom. We chatted. I somehow managed to convince him to come to Arizona. I guess, he liked what I told him when it comes to my advising style and the freedom that he would get essentially to pursue his own ideas. And so it's also like yesterday that January of 2018, that I went to the airport to pick him up. And we went on an adventure, let's say, where I tried to climb a rock, the Javelina rock at the Saguaro National Park, and I was trying to climb it down. It was not easy, and Gabriela actually guided me where I put my footsteps. I remember this. But it's been a real privilege to have had Gabriela as my student. I think, sometimes there's the saying that the student has become the teacher, and I think this is very well fitting in this case. Gabriela has been transformational for my research group. He has accomplished a tremendous amount of science. He has opened up a new field of research in numerical relativity with his accomplishments, and he has taught me a lot, not only research-wise, but also how to approach mentor and mentee relationships. And he's been a driving force, not just research, not just as a wonderful person, but also in leading and efforts in our department that had to do with how to make it more inclusive, how to make it more diverse. And he was one of the founders of the International Scholars Task Force in our department. And he just deserves everything, everything great in his life for everything he's accomplished. So with all of that, I'll just say, Gabriela, take it away.
Thank you very much. Yeah, so I'm very excited to be here to tell you about my research. So today, I'm going to tell you about electromagnetic fields and radiation in dynamical spacetimes, work in collaboration with Vasilis. And I would like to dedicate this talk to the memory of Professor Pieprzocchio, who was one of the first people that got me excited about high energy astrophysics. And excitement is a key word for me, because this is a truly exciting time to work on gravitational physics. Over the past 2 decades, we've made tremendous advancements in our observational, computational, and theoretical capabilities. We have new tools to study strongly gravitating systems, such as the ADS-CFT duality for theoretical studies and numerical relativity for computational ones. And over the past 2 decades, we've also reached terrific milestones, such as the first detection of gravitational waves from the Laser Interferometer Gravitational Wave Observatory in 2015 that detected mergers of stellar mass black holes. 2 years later, we had the first detection of mergers of neutron stars in the 17th of August, 2017, which kicked off the field of multi-messenger astronomy, since we detected gravitational waves as well as the coincident electromagnetic signal. And this is also coupled with the first horizon scale observations of supermassive black holes, thanks to the effort of the Event Horizon Telescope collaboration. So we have new windows to look and study the universe that have never been accessible before. But I don't think this is the only reason. I don't think our accomplishments are the only reason why my community is so excited. I think the key element here, it's what's coming next, because the future is even brighter. Right now, as I'm speaking, we're designing and we're developing the next generation of instruments. Here on the left, I'm showing Einstein telescope. This is one of the 3G gravitational wave detectors. Einstein telescope is going to be transformative and is going to detect every single merger of stellar mass black holes in the cosmic history. So let me stress this again, because it's truly mind-blowing. In 15 years, we're going to move to making our first detection, to making every single detection of gravitational waves from stellar mass black holes. And this is also part of a new generation of gravitational wave telescopes. Here on the right, I have LISA, the Laser Interferometer Space Antenna. LISA is a space-borne gravitational wave detector that is going to see signals from supermassive black holes for the first time ever, providing useful data to study galaxies, to study cosmology, to study fundamental physics. And this is, of course, is not the end of the story. This is going to be coupled with the next generation of electromagnetic telescopes across all the wavelengths, from radio telescopes to X-ray satellites. So we're going to have the best data, the deepest data with highest cadence ever. And this is going to be across all the messenger. This is going to be across all the wavelengths. So this is going to be a watershed moment. We can truly expect our understanding of the universe to be reshaped and revolutionized. And in this, we'll be supported by the growing capabilities in our computation infrastructure. We are in the era of exascale computing, and also with the advancements in machine learning, we'll be able to produce more and more refined models for all these systems and process all this data that is going to come online very soon. So this is awesome. This is why we're so excited. But there's a problem. The problem is we're not ready for that. We have to improve our theoretical models for the extreme universe if we want to take advantage of all these instruments. And let me show a couple of examples. Here on the left, I have one gravitational wave signal as seen by two detectors. The yellow curve is what our current generation of gravitational wave detectors see. And the blue curve is the projected future gravitational wave signal as seen by future detectors. And as you can see, the blue curve is so much nicer, so much better. There is nowhere near as much noise as in the yellow curve. And this is awesome, but this is also a problem because our models for gravitational waves are going to introduce systematics. Our models are not good enough. We're going to be limited by our models, whereas so far we've been limited by the quality of the data, the noise in the data. So if we want to take advantage of the amazing 3G detectors, we must improve our models for gravitational waves. And this is not just for gravitational waves, this is also for electromagnetic waves. For instance, here I'm showing the candidate binary black holes that were found by the Pan-STARRS Medium Deep Survey through electromagnetic means. These are very promising multi-messenger sources. These are supermassive black holes at the center of galaxies. And when they're close, they emit gravitationally, so they are gravitational wave sources, but there's also lots of plasma accreting onto the black holes, so they also emit electromagnetically. These are amazing multi-messenger sources. They're going to produce a lot of useful data for studying the evolution of galaxies, to study cosmology and fundamental physics. But our models for these sources are not particularly good. These are candidate binary black holes. We don't even know if these are truly binary black holes. And the mass and separation I'm showing here, there's lots and lots of uncertainty. So once again, if we want to take advantage of future instruments, if we want to realize the full scientific potential of the technology we are developing, we must improve our understanding of the extreme universe. So this is what I did in my PhD. In my PhD, I advanced the field of numerical activity to push astrophysics, to push fundamental physics, so that we can start moving in the direction of understanding our universe. More specifically, I have 4 directions that I would like to share with you. The first one is going beyond traditional vacuum general relativity. Binary black holes are well described by general relativity, but for future instruments, we'll have to understand all the bumps and wiggles in our waveforms. We'll have to start accounting for effects that we haven't considered so far, environment, dark matter, or parameters that we haven't included yet. So it's important to start moving away from the very clean and relatively simple vacuum general relativity that we've studied so far. Second, I want to deeply understand our foundational theories for the universe, the theory of gravity and the theory of electromagnetism. And to do this, I want to push our theories to the extreme and learn what we can learn when we explore those extreme corners. Next, I want to start connecting with observables, such as for binary black holes with accretion. And finally, I'm committed to making my field more accessible, lowering the entry barrier to this field to accelerate the pace of development so that we are ready, not only when it comes to tools, but also when it comes to people. This is achieved through development of user-friendly codes, through mentoring, and through giving tutorials and stuff like that. So this is my PhD, but this is also the outline of this discussion today. I'm mostly going to focus on part 1 and part 2 today, and I'm going to briefly mention my developments for later 2 parts towards the end of this presentation. So this is my mission, this is my goal, and specifically the system I decided to study to achieve these goals are black holes. Black holes, isolated black holes, are relatively simple objects. We need only 3 numbers to describe them. We need their mass, we need their spin or angular momentum, and we need their charge. And over the past century, black holes have been studied extensively. Theorists love them because they can be described by our fundamental theories, the theory of gravity and the theory of electromagnetism. We call this Einstein-Maxwell theory. And by now, I would say that we have a pretty good understanding of how isolated black holes, and we have a pretty good understanding in their full expression as objects with mass, spin, and charge. And let me share an important result that we found over the past century in this space. We found that there's a relationship between these 3 parameters. We find that there has to be more mass than spin and charge. Or stated differently, there has to be more gravitational attraction than electrostatic and centripetal repulsion. This must be true for our black holes. So now, if we forget about rotation for a second, there's a relationship between charge and mass. So today, I'm often going to think about this quantity, charge to mass ratio, that has to be smaller than 1 for black holes. And here, what I'm measuring is essentially the effect of charge with respect to the effect of gravitational attraction. So again, today I'm going to often refer to this charge to mass ratio. So yeah, isolated black holes, we love them, we understand very well. But the same cannot be said for systems with binary black holes. I'll argue that the nonlinear interaction between black holes is not as developed. We don't understand it as well, especially and crucially when you consider them with charge, with electromagnetic fields. The nonlinear interplay between extreme gravitational and extreme electromagnetic fields is uncharted territory. And there's a lot that we can learn from here. For instance, we can use these systems, Einstein-Maxwell systems, to study specific modified theories of gravity, to study specific theories that I put under the umbrella of exotic physics, of exotic astrophysics. We can even use these systems to study energetic particles, such as the ones in cosmic rays or in particle accelerators, and the production of microscopic black holes, which is kind of cool. And of course, we can use these systems for gravitation with astronomy, and we can use the systems to perform computer experiments where we can push our theories to the extreme and learn what we can learn about fundamental building blocks for our universe, gravitational and electromagnetic fields. So, well, if these systems are so amazing, why this is uncharted territory? Well, the answer is that these are very, very complex systems. When you move from 1 to 2 black holes, this is much harder. There's no symmetries that you can use. There's no perturbation theory that you can apply in general. And the equations that describe these systems are highly nonlinear, coupled partial differential equations that there's no hope we can solve analytically in most cases. So the only resort is to use computer simulations. But even when we move to computer simulation, this is still very hard, to the point that it took 50 years to solve this problem in the case without charge. And there's an entire new field, the field of numerical relativity, that developed out of the attempts at solving this problem. So as a first step in this research, we have to expand and push the field of numerical relativity. To give you a glimpse of what numerical relativity is, we take Einstein's description of general relativity and everything as a spacetime, and we forget about that, quote unquote. We destroy our spacetime four-dimensional description, and we restore an idea of time evolution. So we reconstruct our spacetime one slice at a time. And this is something that we can understand a little bit better. But then when I started thinking about these systems, I realized that numerical relativity was not ready for the field, for the simulations we wanted to do. So I had to extend and develop mathematical and computational tools for simulations of binary black holes with charge. So I had to develop new tools for initial data, new tools to interpret our simulations, what's on our grid, and what we get as observable. And finally, I also had to develop new techniques, numerical techniques, to ensure that our simulations are stable so that we can safely evolve them and find our solutions. So I put all of this, which is one slide but contains a lot of work, inside the Einstein Toolkit. So the Einstein Toolkit is a community-driven open source code for relativistic astrophysics and numerical relativity. It contains a lot of stuff. And over my PhD, I extended it, developed new modules, and became part of the community. I'm going to be technical for a second to give you a sense of what type of simulations we're talking about here. These simulations are simulations on a grid. Typically, this is a mesh-refined Cartesian grid. The type of the equations that we solve are nonlinear, elliptic, and hyperbolic partial differential equations that we solve using pseudospectral methods or finite difference in finite volume. The code is a C++ massively parallel code, Fortran massively parallel code, uses OpenMP and MPI for parallelization. And a typical simulation requires weeks to months to be completed. And here on the right, we can see the logo of one of my packages, Qubit, that is now the official post-processing pipeline for Einstein Toolkit. Okay, now that I have the code, now that I have the technology, my first goal was to use this to constrain charge of astrophysical black holes. So charge, we expect astrophysical black holes to be neutral. The reason is, if they were charged, they will collect charges of the opposite sign, but they will not collect charges of the same sign. So they will quickly discharge. And this is a great theoretical expectation, but we don't have solid observational constraints that this is indeed the case. And this becomes more important when you start blurring what charge is. Charge doesn't have to be electromagnetic charge. There's a whole set of theories that are described exactly in the same way. It can be due to dark matter, specific theories in dark matter. It can be due to specific theories in dark electromagnetism, magnetic monopoles, and even specific theories in modified gravity. For instance, there is a scalar vector tensor gravity that predicts that gravitating bodies have a form of gravitational charge that is controlled by this parameter alpha, and that behaves exactly like an electromagnetic charge. So astrophysical black holes could be charged and could be charged with any of these. So when we constrain charge for black holes, we provide observational support for our theoretical expectation, and we also constrain at the same time all these theories in a new way that was not possible before. So this is very, very useful. And the way I want to constrain charge of astrophysical black holes is by using gravitational waves. So here I'm showing an example of my simulations for mergers of charged black holes. On the left, we have merger with charge. On the right, we have the same system, but without charge. And at the bottom, we have our gravitational wave signal. And as we can see, the gravitational wave signal is different. And this is key. It's different because there is a more energy. There's electromagnetic energy. There's another force. The orbital dynamics is different. And if the gravitational wave signal is different, it means that we can extract charge from our simulations and from our data and constrain charge. So this is what I did. I took GW150914. This was the first confirmed gravitational wave event. Still today, it's one of the loudest, one of the best characterized. It's a merger of nearly equal mass ratio black holes that interestingly also had a coincidental disputed electromagnetic signal. And I use the signal, I look at the gravitational waves, and I place a constraint on charge. When I do so, this is a useful way to perform this constraint, because one, I can target all those theories that I mentioned before in one go. I don't have to specialize my analysis for the different theories that I mentioned before. And second, gravitational waves free stream from the source to us. We don't have to worry about propagation effects. We don't have to model how the interstellar medium is going to affect this. So this constraint is robust and applicable to multiple theories. And this constraint is that the charge to mass ratio for this event has to be of order of 0.2, 0.3, 0.4, depending if you have same charge, opposite charge, just one of the two black holes is charged. Now, if you conjugate this into an electromagnetic charge, then this tells us that the charge imbalance, difference between positive and negative charges in GW15 or N14, has to be smaller than 10 to the minus 17 solar masses, which is quite small. Or if you conjugate this into a constraint in the modified theory of gravity that I mentioned before, scalar vector tensor gravity, we find that the coupling parameter alpha has to be smaller than 0.19, where alpha equals 0 is general relativity, and the previous constraint was alpha smaller than 9. So we improved this constraint by essentially 2 orders of magnitude. And later, a group led by Gregorio Carullo look at the different parts of the same signal, use different techniques to analyze the signal, and found pretty much the same result. Here we can see the solid line is GW15 on N14, and it predicts that the charge for GW15 on N14 should be again order of from 0.2 to 0.4. So we have an external confirmation using different methods and different techniques that indeed this is the result that we can expect from GW15 on N14. So I'm going to quickly start building on my summary, because now we can simulate and analyze these systems. And our first application, we use them in conjunction with gravitational wave data to constrain charge of astrophysical black holes. Now, I'm going to move from this to my second part, where I'll explore how I use the same techniques to push our theories to the very extreme and learn what we can learn about our fundamental building blocks of the universe. So these systems are absolutely awesome because there's not many parameters that we can tweak. We have charge, we have mass, we have angular momentum. That's pretty much it. So we can perform computer experiments where we take two black holes, we smash them very fast one against the other. We take two black holes with a lot of charge. We can do crazy stuff to push our theories to the extreme and see how our theories behave. And we are uniquely positioned to do so. There's no way you can study this with analytical tools. This is the only approach for this corner of the parameter space. And there's lots of important ideas in gravitational and high energy physics that are directly affected by these experiments. And today I'm going to focus on these two ideas, the idea that matter doesn't matter, and the idea of cosmic censorship. So let me unpack them. So the first is the conjecture of matter doesn't matter says that if you have two bodies that are moving close to the speed of light, you make them collide, it doesn't really matter what you're colliding. You can collide black holes, collide boson waves, so it doesn't matter. When you're close to the speed of light, all the observables are going to be the same. It doesn't matter what you have. The internal properties are not important. And this, over the past 2 decades, have been verified numerically for a lot of systems, but we still don't know if charge matters. If you have a merger of charged black holes, does charge play a role or not? And there's good reasons to believe that charge may play a role. One is that charge is conserved. Two is that charge is a new emission channel, you have electromagnetic waves. And it's very important to understand how this conjecture behaves and if this conjecture is broken when you include charge, because this idea is used in high energy physics, is used in microscopic black holes, is used in the Large Hadron Collider to make estimates of the rates of production of microscopic black holes. And particles have charge. So we have to understand if charge matters in high energy collisions. The second idea I'm going to explore today is the idea of cosmic censorship. This idea says that if you have a singularity, a place where our laws of physics behave well, you have to have an horizon to protect this singularity. So this is our black hole. And if we were able to look inside, we'll see this. We'll see a singularity. Now, when you increase charge or you increase spin, what you're doing, you're making the size of the horizon smaller and smaller. And if you put too much charge or too much spin, the horizon disappears. We call this a naked singularity. And the idea of cosmic censorship says, no, this is not allowed. We cannot form naked singularity. And once again, this idea has been explored extensively over the past decades. And we've not been able to break cosmic censorship, but it's critical to keep understanding if there's ways where, or corners of the parameter space where this conjecture could be violated. So it's important, and it's important to test with more and more systems. And every time we'll learn something new, because we'll learn how nature finds a way to protect cosmic censorship. So today, I'm going to discuss these two conjectures. For the first one, let me show you an example where charge matters. So here, I'm taking two black holes, and I'm letting them go. They are going to collide because of their gravitational attraction. And this is the gravitational signal that they produce. Now, I'm going to repeat the same experiment, take two black holes. Now I put a little bit of charge. Let's see what happens. When I repeat the experiment, I get that my gravitational wave signal is different. So we can say that in low energy collision, and this is low energy because I just let my two black holes merge. In low energy collisions of black holes, charge matters. We expect that, and we find that this is indeed the case. External observers can tell that there was charge. Now, let's repeat this experiment with high energy collisions. I'm going to push the two black holes. And here I'm pushing them at 60% of the speed of light. And what I see is that no matter how much charge I put, I'm always finding the same gravitational waves. This tells me that external observers are not going to be able to tell if there was charge or not. This tells me, once again, that charge doesn't matter in high energy collisions. And this is an important result, because we can go back to all the previous studies that ignore charge, studies about microscopic black holes, about production rates, and we can say, okay, those studies are safe. We don't have to worry about charge. Charge indeed doesn't matter. And this is nice. So from here, we can look at the other conjecture, the idea of cosmic censorship, because when our black holes merge, they also lose energy. They lose gravitational energy. So what if we make them merge so fast that the energy that they lose is such that the remnant ends up much lighter, and since charge is conserved, I'm going to have a remnant with charge to mass ratio larger than 1. The cosmic censorship will say, no, this is not allowed. So the idea is, again, energy is lost in the collision, but charge is not. So maybe we can push our charge to mass ratio to be larger than 1. So there's a region in my parameter space. On the x-axis here is how strong I push my two black holes. On the y-axis, I essentially have the size of the final horizon. And there's a region where we'll have naked singularities. Can we enter that region? And to answer this question, my strategy was the following. First, I developed an analytical method using conservation laws to make a prediction about the outcome of this process. And then I use my full numerical relativity simulations to verify if my model indeed is correct. So let's see what happens. So here we have the prediction of my model. For increasing values of my push, I find that the size of the horizon gets actually larger and larger. And we can understand that. And also for different values of charge, what I see is that I can never really enter the region for where naked singularities are produced. So let's first verify that this is indeed the case, and then let me explain what's happening. And here I'm very excited to share what was one of the highlights of my PhD when I ran my simulations, and I found this. And I found that my model perfectly predicted the outcome of my simulations. That felt very good. And so what's happening here is that the more we push our black holes, so when we move towards the right of this plot, the more energy we're injecting in the system. So the effect of charge is washed out. And that's why we shouldn't be too worried about formation of naked singularities. And if we were to look carefully at the case that looks like it's almost to cross the line, well, we wouldn't find that there's no formation of naked singularities in that case either. So we can say that in this case, cosmic censorship is saved. Okay, well, the reason why cosmic censorship was saved here is because our system became so extreme, the charge stopped being important. So let's look at a different way where we could produce a naked singularity. Here is a quasi-circular merger, where I crank up the amount of charge. And the reason this is interesting is because when I have a quasi-circular merger, there's angular momentum, which is a parameter that I didn't have before. So there's a new pathway to produce naked singularities. So I'm going to follow the same script. I'm going to develop a new analytical model to predict the properties of the merger remnant. I'm going to verify numerically with my full simulations that the model works, and I'm going to argue what that entails for cosmic censorship. So this is the outcome of my analytical model. So as I increase the amount of charge, which is on the x-axis, I get a prediction for the amount of spin, angular momentum, and the amount of charge that I have in the remnant. And since I have the technology to verify that this prediction is right, I performed full numerical simulations. Once again, I found very good agreement. So I can safely expect this model I can use this model to discuss cosmic censorship. And when I do so, when I look at the size of the final horizon, this is what I find. Once again, we have a region that we are trying to get in. And no matter how much charge we put, no matter how hard we try, we're always outside of this region. But here, it's interesting to learn why this happened. It's no longer because the system was extremely dynamical. It's the opposite. When you have more and more charge, the system becomes gentler and gentler. There's less and less emission. Everything takes longer. It's much more relaxed. So in this case, the system is not very much dynamical, and we see that we cannot make our final horizon disappear. We cannot form naked singularity in this case. So once again, cosmic censorship is saved, and in the process, we'll learn new ways. We'll learn how nature saved itself from producing naked singularities. So once again, and I'll keep building up my summary. We perform computer experiments with these systems to test whether charge matters in high energy collisions. It doesn't, and whether we can form naked singularities. We can't. So let me quickly go through my last two sections, because I also developed new tools within the Einstein toolkit to perform numerical simulations of accretion into binary black holes. On the right here, we can see one of my simulations after merger. I have new ways to produce initial data to understand what's in our simulation, new diagnostics, and new ways to look at observables. And this is important work for the LISA collaboration, laser interferometer space antenna, because this is going to be one of the prime targets. And among the tools I've developed, there's a new ray tracing code called K-Ray, which is part of a larger collection of codes that I developed during the years. They're all open source codes. They're all designed to be accessible, user-friendly, and to lower the entry barrier to my field. In this, I also gave lots of tutorials. I mentor students, and I try very hard to lower the entry barrier to numerical relativity. So with this, I'm quickly going to conclude by finishing building up my summary. We can now simulate important targets for the LISA collaboration, LISA interferometer space antenna. And we have new tools perform these simulations that now hopefully new students can use to get to the science more quickly and effectively. And with all of this, you probably realize that I haven't solved the problem that I posed at the beginning. We're still very far from having solid models for the extreme universe. There's still a lot of work. So this is just, if you want, the first step in improving our models for the extreme universe so that we're ready for the future for us. So I'm going to conclude by acknowledging that all of this was possible because of computational time and funding, particular from the Texas Advanced Center for Computing and from NASA. They gave me fellowships. And well, and also the Einstein Toolkit collaboration that it was critical in enabling me to perform this research with their open source code. And during my PhD, I definitely learned that while money and computational time are amazing, what's even better is people. So I really have to thank all the people that I've met along the way, particularly the GR Generativity group at the University of Arizona and the Event Horizon Telescope group, CK, Dimitri Sanfrial, that welcomed me from my very first day. And I'm going to go over by 1 minute to tell you a very quick story. This is a story of a mountain. Well, this is Mount Lemon, a picture I take every day when I go home because it's so beautiful. It's a mountain that we have here in Tucson, and I really wanted to climb this mountain with my bike since coming to Tucson. The first time I tried, I couldn't get past 1/3 of the way. I got a flat tire, but I was so happy because I had to come down. I knew I couldn't make it. But later, a few months later, Vasilis sent me an email saying, how about we try together? So Vasilis and I tried to climb the mountain together, and we reached much further than I did by myself. We didn't quite reach the summit, but later I did conquer Mount Lemon. This is a picture of me on top of the mountain with my bike. So of course, this is not a story of me conquering like a literal mountain. This is a story of me conquering a figurative mountain that is my PhD. And I really have to thank Vasilis' guidance and support here throughout my PhD. So thanks, and I'm happy to take